Today, we're taking a close look, a really granular look, at liquefied natural gas, or LNG.
Right.
But we aren't here to just talk energy basics. We are diving into this intense wave of innovation that's pushing the industry toward a really critical milestone in 2026.
And our mission for this deep dive is to pull out the key strategic knowledge.
Exactly. The technological and business advancements that are happening right now across the whole value chain.
From production to shipping, all the way to the digital intelligence that's managing it all.
And it's not just a technical exercise, is it? This is about strategy.
Oh, it's a strategic necessity. LNG is really serving as the perfect example of a bridge fuel globally.
A bridge fuel.
Yeah, I mean, you look at the pressures of the energy transition, and LNG offers this reliable option with, significantly lower emissions than coal or heavy fuel oil.
And its growth helps with energy security too, I'd imagine.
For sure. It diversifies supply away from just traditional pipelines.
Okay, so that immediately brings up a question for me. This kind of rapid innovation, it must cost serious capital.
It does.
So what are the macro forces pushing an entire industry to move this fast?
You can really boil it down to three intertwined drivers. First, there's the powerful economic imperative.
Money.
Always. Companies are just relentless. They have to slash both capital expenditure.
How much it costs to build the plants.
Right. And operational expenditure, which is what it costs to run them. And critically, they need to monetize stranded gas reserves.
Those deep sea fields or remote pockets that are just too far from a pipeline.
Exactly. So if the gas can't come to the pipeline,
the processing plant has to go to the gas.
And that's where you get floating LNG facilities, or FLNG.
Okay, that makes sense. What's the second force?
The second is undeniably environmental. We're seeing these really stringent, complex regulations coming in, especially for maritime transport.
Forcing a shift to cleaner fuels.
It is. And then the third driver is just pure technological progress. I mean, the advances in process engineering, material science, digital tools, that's what makes the economic and environmental goals actually feasible.
So which one is the bottleneck right now? Are the regulations moving faster than the engineering, or is it still all about the capital?
It's the tension between the first two. The capital is there, but it's only flowing to proven, ultra-efficient technologies. So engineering excellence, that becomes the real differentiator. You just can't afford to build a traditional, less efficient plant today. You have to leapfrog.
Let's talk about that leapfrog in production. Liquefaction it's brutal. You're cooling gas to, what, minus 260 Fahrenheit?
Roughly, yeah. The energy bill for that alone is astronomical.
So where's the innovation there?
It's in something called process intensification. Engineers are moving toward these next-gen processes, often using advanced mixed refrigerant cycles.
Right.
The whole objective is to dramatically reduce the specific energy consumption.
Which is just how much power you need to liquefy a standard unit of gas.
Exactly. How much power per unit? And that saving translates directly into lower OPEX.
And we mentioned FLNG earlier. On those giant floating facilities, space is so tight that efficiency must be even more crucial.
It is paramount. For the biggest FLNG projects, the dual mixed refrigerant, or DMR process, is heavily favored.
Why that one specifically?
It uses two separate cooling loops, and it's known for its incredibly high thermal efficiency. It maximizes the output you can squeeze into a limited space on a ship's hull. It's all about compact power.
And this is where I found a really surprising fact in the source material. Climate, of all things, can offer a strategic advantage.
Yes, ambient temperature.
Right. It turns out that operating these liquefaction plants in colder places, say the Arctic, can give you a 20 to 26% energy efficiency gain.
A substantial gain. And a corresponding drop in CO2 emissions compared to running that same plant in a hot tropical region.
That's a staggering climatic bonus. It gives a project like the Yamal LNG plant a massive competitive edge.
It absolutely does.
Right.
But leveraging that geography introduces some extreme material science challenges. We're talking about cryogenic engineering under immense stress.
So it's not just building something strong, it's building something that can handle those sub-zero temperatures without failing.
Exactly. You need advanced insulation materials that not only perform but survive. We're seeing breakthroughs in things like reinforced polyurethane foam and cellular glass.
And these materials are essential for what, two main reasons?
Two reasons. Minimizing the heat leakage that threatens the liquid state and just maintaining structural integrity in that constantly freezing environment.
Wow.
They even have these incredibly detailed insulation procedures for every single component, valves, flanges, you name it, just to guarantee the facility's quality in those polar climates.
And beyond the structure, managing that temperature is critical for another reason, preventing product loss.
Right. Which brings us to the infamous issue of boil-off gas.
The lost gas.
Yes. So when external heat inevitably leaks into those ultra-cold LNG tanks, some of the liquid, it vaporizes.
And that vapor, the boil-off gas, or BOG.
It's a double whammy. First, it's lost cargo, so it hits your bottom line. Second, it's a big environmental concern.
Because it's mostly methane.
Which is a greenhouse gas far more potent than CO2, at least in the short term.
So mitigating BOG becomes this necessary innovation across the entire supply chain, starting right at the export terminal.
At the terminals, the focus is on capturing that vapor, either with reliquefaction or with subcooling systems.
And which is better?
Well, standalone subcooling, where they chill the LNG just a bit more before loading, is proving to have really substantial economic benefits. Less vapor, more product ready to go.
And what about further down the line? Like at a refueling station for LNG trucks or ships, you can't put a giant reliquefaction plant there.
No, you can't. And that's where innovation meets local economics. For those smaller stations, the most viable solution they've found is to capture that boil-off gas and convert it into compressed natural gas, CNG.
Ah, so you're turning a waste product into a new product.
Precisely. It fundamentally changes the profitability for small operators. You're turning a potential loss and an environmental liability into something you can actually sell. It's like monetizing the steam from your coffee.
That makes perfect sense. Okay, shifting to transportation. The ships themselves are the next big area of innovation.
Indeed. Especially with those strict maritime regulations we talked about.
So modern carrier design has to balance safety, efficiency, and compliance above everything.
It does. And for propulsion, the industry is really standardizing on dual fuel diesel engines, the DFDEs.
I know.
They're currently the most economic and regulation compliant choice. They run mostly on natural gas, but use a tiny bit of heavy fuel oil HFO to ignite the mix.
And that dramatically cuts down on emissions.
Right. Huge reduction in SOx and NOx compared to old HFO-only ships, while still keeping fuel costs manageable.
But the journey itself has this serious inherent safety challenge.
Yeah.
Sloshing.
Yes. That uncontrolled, violent movement of liquid in a partially filled tank, it can literally cause structural failure.
It's a critical concern then.
A huge priority for research. We found details on a major project called Sloshel. It investigates the behavior of these corrugated primary membranes.
What are those?
They're thin, flexible internal walls inside high-tech tanks like the Mark III systems.
And why focus on those corrugated membranes specifically?
Because they're worried about peak load events. They're studying how these membranes react to intense impacts, like a breaking wave that forms inside the tank.
A wave inside the tank.
Yeah, the research simulates the wave crest, jet formation, and trapped air. It's incredibly complex. The goal is to build models so you can guarantee a new ship's containment system can resist those maximum slosh loads.
So it's about anticipating catastrophic stress at the micro level of the tank wall. And of course, you still have to manage boil-off gas during transit.
Which relies on better insulation and those more efficient onboard reliquefaction plants.
Okay, let's pull back to the big picture. This sounds like an unbelievably complex logistical chain.
It is.
From an Arctic well to liquefaction, across an ocean, to a local refueling station. What kind of intelligence manages all that at once?
This is where the industry is pouring massive investment into what they call the digital control tower.
A digital control tower.
Think of it as a sophisticated command center providing centralized, real-time operational intelligence. It integrates data streams from engineering, construction, logistics, live shipping data, all into one platform.
So there's also the digital twin technology we hear about, but for an entire global enterprise.
That's a great way to put it.
What's the real advantage there?
It's all about risk management and optimization. With a digital twin of the supply chain, you can model scenarios, predict failures, and instantly re-optimize resources. You eliminate costly delays. Because you can see in real time if one part, say a specialized valve from Europe, is delayed, and you immediately recalibrate the construction schedule in Southeast Asia.
And how is AI being used for day-to-day operations, predictive maintenance, that sort of thing?
It's driving a revolution in automation. IoT sensors and data analytics mean reactive maintenance is becoming obsolete. Now, it's all predictive.
Can you give us a specific example?
Sure. A really interesting one is using machine learning algorithms like the random forest method to accurately transfer temperature load profiles between different complex modeling software platforms.
That sounds incredibly technical. What does that mean for us?
Think of the AI as a high-speed, ultra-precise translation engine. When you're designing a new LNG bunkering facility, a refueling dock, you use one piece of software to model how a cold liquid spill will affect the structures. Then you need to apply those temperature findings to another piece of software that designs the safety systems, like cryogenic spill protection.
And the AI makes sure that translation is perfect.
Perfect and precise. It ensures the safety plans are perfectly sized for the real world, eliminating human error and speeding up the whole design process. The facility is instantly safer and faster to approve.
That focus on optimization is clearly central. But as we synthesize all these technical gains, we have to talk about the environmental nuance.
Of course.
LNG is cleaner than HFO, but it's still a fossil fuel.
Absolutely. The positive impact is undeniable for air quality. LNG practically eliminates SOx and NOx. And compared to conventional marine fuels, you get a solid 20 to 30% reduction in CO2. It's vital for cleaning up the maritime sector.
But the big caveat, the critical one, is in the full life cycle analysis, from the well to the wake of the ship. Where's the vulnerability?
The vulnerability is the persistent problem of methane slip. This is the uncombusted methane, the natural gas itself, that gets released into the atmosphere, either during liquefaction or more often during the final combustion in the ship's engine.
And since methane is such a potent greenhouse gas, even a small leak can erode or even cancel out the CO2 benefits.
Precisely. It all depends on operational factors. That's why the full life cycle analysis is so crucial. The amount of methane slip varies dramatically based on engine type, high pressure, low pressure, and operational efficiency.
So the industry has to constantly minimize that slip.
Aggressively, at every single stage, to make sure LNG keeps its value proposition as a bridge fuel.
And while the engineers solve those problems, you still have these huge logistical and regulatory challenges for global expansion.
That's the management hurdle. On the logistics front, if LNG is going to be a widespread transport fuel, you need these impossibly complex location routing and inventory models.
It's an optimization nightmare.
It really is. Think about managing the entire distribution network to meet uncertain demand across dozens of different ports.
And regulation is always trying to catch up with technology.
Always. There's a constant need for international regulatory harmonization. Specifically, updating things like the IGF code, which is the safety code for ships using gas fuels.
So as new technologies emerge, the global safety rules need to adapt just as quickly.
And consistently, to make sure these innovations are safe everywhere in the world.
Which brings us to the end of our deep dive. The story of LNG innovation towards 2026 seems to be driven by this incredibly high bar.
A convergence of forces.
The need for relentless economic efficiency, mandated safety, and tightening environmental rules. We've seen sophistication integrated everywhere, from using Arctic geography to installing digital control towers.
The industry is definitely showing its resilience and technological power, cementing its role as a necessary bridge. But that raises an essential and I think a provocative question for you, the listener, to consider.
Go on.
Given the massive investment being poured into this LNG infrastructure right now, how rapidly will the industry need to pivot past 2026, past these bridge solutions, to genuinely zero carbon fuels? How do they avoid locking in technologies that, while cleaner than oil, are still fossil-based?
So the focus has to stay on solving that methane slip problem.
That is the real test.
Food for thought indeed. Thank you for joining us for the deep dive.